Welcome to this explainer. Okay, today we're zooming in on a tiny, incredibly unassuming component. But don't let its size fool you. This little guy takes raw, uncontrollable, and frankly dangerous electrical power and completely tames it. It turns it into the precise, manageable force that literally runs our modern world. It is the hidden foundation of electronics, and I guarantee there is one sitting right within arm's reach of you right now.
Here's our roadmap for today. First, we'll uncover the hidden electronic hero. Next, we'll be decoding Ohm's law, followed by the anatomy of a fixed resistor. Then we'll look at heat and voltage drop, and finally, we'll map out the resistor family tree.
Section 1. The hidden electronic hero, the unsung foundation of modern electronics.
So I've got to ask, have you ever stopped to think about what actually controls the electricity in your gadgets? I mean, when you press a button on your smartphone or boot up your laptop, there are invisible forces at work right there in the palm of your hand. Because, electricity naturally just flows wherever it can. It's chaotic. It needs a manager. It absolutely needs a controller.
Now, for well over a century, as our absolute reliance on electricity exploded, we desperately needed a way to rein in and control that electrical current. And that is exactly why the resistor was invented. And what's wild is that while resistors come in all sorts of crazy shapes and sizes today, their fundamental purpose hasn't changed a bit. They exist for one simple reason: to resist the flow of electric current. And by doing so, they perfectly manage the voltage and current throughout an entire circuit. Section 2. Decoding Ohm's law. The science behind the resistance.
All right, to truly get how this works, we have to talk about the math. The absolute crucial point here is Ohm's law. It formally states that the current flowing through a conductor between 2 points is directly proportional to the voltage across those points and inversely proportional to the resistance.
Okay, I know that sounds like a bit of a mouthful, so let's break that heavy math down into some simpler mechanical analogies, because honestly, this is where it really clicks. Think of voltage as the push. It's the muscle driving the electrons through a circuit. Then we have current, which is the actual flow of those electrons. And finally, resistance. Think of resistance like friction in the mechanical system. It's actively opposing that flow. So a resistor is basically a tiny device specifically designed to provide that friction. It dictates exactly how much current is allowed to flow for a specific amount of voltage push.
Section 3. Anatomy of a fixed resistor, peeling back the layers.
Let's zoom in from the abstract math to the actual physical component. There are 3 main layers to your standard fixed resistor. Starting right in the center, at the core, we have the resistive material. This is crafted from materials picked specifically for their innate ability to restrict electron flow, stuff like carbon, metal film, or wire-wound elements. Extending outward from that core, we have the leads, or terminals. These are just the metal wires acting as the physical pathways for the current to actually enter and exit the resistor so you can, plug it into a circuit. And finally, encapsulating the whole shebang is the outer protective coating. Usually made of ceramic or plastic, its whole job is to protect that highly sensitive resistive core from nasty environmental damage, like moisture and excess heat.
Section 4. Heat and voltage drop. The effects of opposition.
Now, when electricity fights its way through that resistive friction we just talked about, we get 2 really distinct effects. First up is heat dissipation. The resistor actually converts some of that electrical energy directly into heat. In high-power circuits, these guys can get shockingly warm. Actually, scratch that, they can get blazing hot, sometimes even needing dedicated heat sinks just to keep from melting down. But the second effect is voltage drop. Because the resistor is actively impeding the current, it causes a calculated reduction in voltage across its terminals. And listen, this isn't some annoying side effect, it's a vital feature. This exact voltage drop is what allows us to safely step down the power going into incredibly delicate components, like the microchips powering your computer. Without it, they'd fry in an instant.
Section 5. The resistor family tree. A type for every application.
What's honestly so fascinating here is how manipulating such incredibly simple physics has led to an entire family of highly specialized tools. For instance, we have fixed resistors, which provide a constant, unchanging resistance to keep standard circuits perfectly stable. Then we have variable resistors. These actually let you manually adjust the resistance on the fly. Think of a potentiometer, like the volume dial on an old-school radio.
And then it gets even cooler with specialized resistors, like thermistors. These brilliant little devices actually change their resistance based on the ambient temperature around them, which makes them absolutely perfect for environmental sensing. It's a technology that is universally simple at its core, yet endlessly adaptable for keeping things safe and efficient.
To wrap up our explainer today, I really want to leave you with this thought. Understanding and manipulating the basic principles of physics, like Ohm's law, can lead to devices that power modern life. The resistor is truly a textbook example of this profound simplicity. It is a tiny, unassuming, yet undeniably vital piece of engineering that makes our entire modern electronic world possible. So the very next time you pick up your smartphone or turn on your television, ask yourself, what other invisible laws of physics are silently powering your world right now? Thanks so much for learning with me today. Stay curious and keep exploring.